This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to section 5.5, finding log function values on a calculator. On a calculator? Are you serious? There are some things that that this textbook does really well, and naming their sections is not one of them. Okay, so I'm just going to start off with that this section is not all about finding stuff on a calculator. It's really about something deeper than that. But in order to get there, what I'd like to do is first talk about something called growth factor. Growth factor is, let's say you had $100, and if you multiply it by 1, you're still going to have $100. That's no change. I mean, that's just multiplication. Multiply anything by 1, and there's no change in it. You get the same output as you put into it. Anyway, but if you wanted to increase something by 1%, you could multiply it by 1% more than 1. You could multiply it by, say, 1.01. And that would produce a 1% increase. Multiply, if you want to increase by 2%, that would be multiplied by, not by 0.02, like that would be the 2%. 2% written as a decimal is 0.02. So you don't multiply by 0.02 to increase it. You could multiply by 1.02, and that would produce something just a little bit larger. It would be a 2% increase. Similarly, you could take the number 1 and subtract 1% to get your growth factor that you would need. These are all growth factors. $100 times 0.99 will give you the $99 that you need to represent your 1% decrease. Same thing, 0.98 would be a 2% decrease. So with this idea of growth factor, I really like this because it's a two-step process, and the first step is easy enough to do in your head. And I don't say that lightly. I'm not a teacher who wants you to do lots of things in your head, but this is one thing you can do in your head. You can figure out the growth factor. And then the second step is multiplying. Often teachers describe this process in the opposite direction. If you want a 2% increase, it would be $100 times the decimal form of 2%, and then you add it on to the original. Well, I think you should do the addition first. I think you should take 1 plus 0.02, and you get 1.02. That's something you can do in your head. You multiply it by 100, you get 102. Anyway, I'm going to use this idea of growth factor to introduce a concept of E, but let me show you what that means first. Let's say you had a $75 dinner, and then you had to add a 7% tax and a 15% tip. Well, you can start with a $75 dinner, and then you can multiply it by 1.07, the increase of the 7% tax you need. And then you multiply it again by 1.15 to produce the 15% tip. These growth factors can get stacked on top of each other. You can start with the original and growth. You can increase it or even decrease it as many times as you want just by tacking on as many growth factors as you need. They stack on really well that way, and you can just type them all into your calculator once and hit enter. So check this out. What if you invest money at 2% interest on $1,000 for 1 year? That'd be your growth factor would be 1.02. $1,000 times 1.02. What if you did the same thing and you spread out the interest semi-annually? Meaning, you're going to get this interest, this 2% interest, spread out over the course of a year, semi-annually. That means 2 times. Well, you get half of your 2% interest once, and then half of it again the next time. So basically, the formula becomes, this is your $1,000 times 1 plus half your interest, and then again 1 plus 0.02 divided by 2. That's half your interest. What if you do the same thing except spread out monthly? 2% interest for 1 year, spread out monthly. You would have your original, and then every month you would multiply it by a very small growth factor. It would be 1 plus 0.02 divided by 12. But you would get it 12 times. So in the end, you're actually getting more money than you would if you only spread it out twice or just got it once at the end of the year. Basically, an easy way to write that would be $1,000 times 1 plus 0.02 over 12 to the 12th. It's over 12 because you're taking the 2%, you're spreading it out. You're getting, this is 1/12 of your interest, and then it's spread out over 12 periods. So you have 12 of these growth factors stacked on top of each other. $1,000 times all of this to the 12th. So that's how we get this formula. This is A of t, where t is the time, how many years, and A is going to be the final amount. If you want to know what your final amount is, you start with a principal. That's a starting amount, P, the principal amount, and then T is, like I said, years in the bank, and that's up here. And then rate, and the word problem will almost always give it to you in terms of percent. You need to convert that to a decimal and put it right here. Then N is going to be the number of times interest is compound per year. So if you're getting it, every month, then make sure N is 12. R divided by 12, and 12 is up here too. So if you're going to use the formula, you can just say $100,000 invested at 6.5% semi-annually. 100,000 goes out in front. 1 plus percent written as a decimal. Semi-annually means over 2, and then 2 semi-annually twice a year. 2 goes up there, and then this T is, you can use this T to figure out however long you want. T can be the input, and then the dollars would be the output. Quarterly would look like this. 4 times a year. Monthly, we already did. So that's what your amount can look like. Let's take this. Your starting amount, P, is $1, and if it gets 1 year in the bank at 100% rate, and this is not, I'm doing this not because it's realistic at all. No bank will ever give you 100% rate. But I just want to do this in order to illustrate one final idea that we're trying to get at. 100% rate is 1 plus 100%, meaning it doubles. After 1 year, it should double. So, compounded annually, that means once, your money will double. It's 100% interest. You go from $1 to $2. Yay. But what happens as N increases? That means if you're compounding it more and more frequently. Well, if you get it compounded just once, at the very end of your year of investment, you get an additional $1. It doubles up to $2. But if you compound it twice, once halfway through the year and then once in the end of the year, this number actually increases to 2.25. 3 increases 4 compounded quarterly gives you this. If you spread out your 100% interest over the 4 different seasons of the year, the 4 different quarters, then you get 1 plus 1 over 4 to the 4th, which actually turns out to be 2.44. 5 compounding periods here. You spread out the year into 100 compounding periods, basically every 3 point whatever days, then you can say you get 2.7. And the more compounding periods you get, the higher the amount is. It's not going to increase forever. Here's compounded daily, 2.7146, 300. That's 365 compounding periods. If you multiply that by 24, this is, if you get interest, a tiny fractional, minuscule amount of interest every hour of the year. That turns out to 8,760 hours compounding periods. That turns into 2.7181. Now, these numbers are all increasing, and if you compounded by the minute, it would give an even slightly higher number as well. But what you might notice is that it's got a horizontal asymptote right here. You're starting out very low, and then eventually, the more compounding periods you get, the closer you get to this crazy number right here. And it's actually, if you type this number into Desmos, it's actually previously stored in. It's such an important number. It's kind of like pi. You remember pi, 3.14159265359. It keeps going. It's an irrational number that has lots of applications in geometry, particularly with circles, diameters, spheres. They all rely on pi. And pi is such an important number that it's the Greek letter p. We just reserve that to mean this irrational number, and it's programmed. You can just type it in pi into Desmos, and it automatically remembers. Well, that's a crazy number. Same thing with what we're going to call the letter E. E for Euler, the guy who developed a lot of these applications. So if you just type in E into Desmos, it remembers 2.718281828846, and it's an irrational number, never ends, no perfect decimal representation. But your textbook says it like this: E is equal to 2.718, and it keeps on going. The thing to remember about E is that it's just a number, and you can approximate it as 2.7. Check this out. So most calculators, and this is where the title of our section comes into play, most calculators do have an E button, not a capital E, but a lowercase e, and e to the first power looks like this, and the instructions say to round to 4 decimal places, so we get 2.7183. I just want to take a moment to say that zinc is the audio check element for today. Zinc is your element, so make sure when you get to the end, you choose zinc. E to the third is 20.0855. That's rounded, and it's this section. These problems get a lot easier when you remember E is just a number. It's about 2.7. 2.7 to the third power is about 20.0855, and it's something you can type this into a calculator also. 0.7945. E to the 0 is 1. Anything to the 0 is 1. But it's particularly 2.7 to the 0 is 1 as well. And so I want you to tell me what E plus 1 is. E, it's just 2.71828182846. It keeps on going. Natural logarithms. That is logs of base E. Now, we already know that log base 10 is an incredibly common log. So common that if you just see log of x, you can assume that it's a 10 that's unwritten as the base. Well, the second most common logarithm that we have is log base e. And so instead of writing log base e all the time, we just write what's called a natural logarithm. And there's a story behind why logarithms are called natural logarithms here. The natural log is the log that takes a base e. But for any of you who take Romantic languages, you know that the adjective comes first. So, the adjective comes second. In English, the adjective comes first. So we call it a natural log. But when you write the abbreviation, like the French did when they first started developing this in the Swiss, then you can say it's a logarithm. What kind of logarithm? The natural logarithm. So logarithm naturel x means log e of x. And that just means log of base e. So, if we're going to convert this to logarithmic notation, then what this would look like, e to the third, the base switches, the power switches, and then you get log base e of x is equal to 3. What's the exponent? It's 3. Now, no one writes log base e to the x equals 3. It's commonly just natural log x equals 3. And here, base is e, exponent is x, power is 100. The exponent goes by itself, and you have the logarithm naturel of 100. Base, exponent, power. Unwritten base is e, exponent, power. The natural log of 1 is equal to 0. Here, we got a base of e, exponent of 1, and power of 2.7. And if you switch them, you get the natural log of 2.718281828846. If you take the natural log of that, you get 1, because 1 would have to be the exponent. For each, evaluate with a calculator and also convert to exponential notation. So check this out. I want to do 2 things here. I want to take this and take the natural log of 645,778. What would the exponent have to be in order to produce a power of 645,778? The exponent would have to be 13.378. And you can check that by rewriting it as an exponential notation. E to the 13.378 is approximately 645,000. Here, what would the exponent have to be in order to produce an incredibly small number like this? Well, your exponent would have to be negative. In fact, you take the natural log of that, and you get negative 10.64. Rewriting it in its exponential notation, what that means is e to the negative 10.64 is approximately 0.40239. What's the natural log of negative 5? That means what exponent would you need in order to produce a power of negative 5? Well, that's undefined. There is no answer. There's no number. There's no exponent that you could put on top of e to produce negative 5. And you can see there's no solutions to this. So therefore, the natural log function is undefined. The natural log of e, well, what exponent would you need in order to produce a power of e? You would need 1. And so you can type it into a calculator as natural log of e equals 1, or you could also say e to the 1 is equal to e. The natural log of 1, so what exponent would you need in order to produce a power of 1? Power of 1, base of e, that you would need an exponent of 0. That's why x equals 0. And that's all we got for this page. But hold the phone, we've got a third page. Good night. This is going to take forever. No, it won't. Change of base formula. Check this out. For any logarithm bases a and b, for any positive number m, if you need to change the bases, let's say your calculator doesn't work, you can't program in some random base 3 or base 5. It only has a log of base 10. What you can do is you can change the base. You can change the base to whatever you want. So check this out. If you have a log 5 of 8, then you can use the formula to just say this is equal to log base 10 of 8, log base 10 of 5. The 5, what used to be the base, now becomes the denominator. Log 8, log 5. And even more than that, you can take the log, you can say that there's an exponent on this. 8 is really 2 to the third. So say this is 3 log 2, log 5. That's how it simplifies. Here, log base 4 of 100, you can just change the base to base 10, and that's actually super convenient because you've got a log of 100 on top. So what exponent would produce a power of 100 when the base is 10? So the exponent would be 2. Log of 4 is the same thing as 2 squared. Where did this denominator come from? It came from the change of base formula. The 4 used to be a base, and now it's the denominator. The new base is 10. Log of 2 squared, well, you can just take the exponent, move it out front. You get 2 over 2 log 2. And the 2's cancel, and you just have 1 over log base 2. 1 over log 2, the base is 10. Same thing here. I think the easier way to do this problem is to say that you could have, it's just to write this as the exponential version of the equation. But if you wanted to, you could change the base. Log of 32, that's the base, the unwritten base is 10. Unwritten log base 10 is 2 of 2. So then what you get is you get log of 2 to the 5th. 32 is just 2 to the 5th over log 2. Bring the exponent out front, and you get 5. Log 2 over log 2, you just get 5, which is what the exponential version of this equation would produce as well. Same idea here, same logic. You get log base 3 of 81, and in some calculators, they don't allow you to program in log base 3. So what you can do is you can just say that change the base to base 10. Log base 10 of 81. Log base 10 of 3. 3 used to be the old base, and now it's the denominator. But 81 can be written as an exponent, that's 3 to the 4th. Bring the 4 out front, because an exponent on the inside becomes multiplication on the outside. 4 times log 3 over log 3 just gives you 4. Find each using natural logs. So we're going to take, I want you to notice this, log base 5 of 8, log base 5 of 8, log base 4 of 100, log base 4 of 100, log base 2 of 32, log base 2 of 32, log base 3 of 81, log base 3 of 81. What we're going to do is we're going to change these, we're going to choose natural logarithms now. And we should get the same answer. It actually doesn't matter which base you change it to, the logarithms are all, the final answer is going to be the same. So here you can change it to log of 8, a natural log of 8 over a natural log of 5. The base is e. And if you continue on in the same logic that we used before, we got 2 to the third. The exponent here moves out front, and you get 3 natural log of 2 over natural log of 5. You type that into a calculator, you get a decimal equivalent of something approximately 1.29, which, if you type in the above version, you get the same decimal approximation, about 1.29. The log base 4 of 100, you get the natural log of 100 over a natural log of 4. You can change it to whatever base you want, the natural log or base 10. So we get natural log of 10 squared, and then natural log of 2 squared. That becomes 2 natural log of 10, 2 natural log of 2. Canceling out the 2's, you get natural log of 10 over natural log of 2. You should start 5e1, copy the problem list, do the first problem. I'll see you in class. Sorry the video was so long, but I do think that you would enjoy having no videos tomorrow night. So take care, and I'll see you in class.